the value. So here that value comes. So you know this is the variation. So this can also be used if you don't have the facility. Again, this is app based. How many of you have seen Minority Report? Tom Cruise. So he predicts, this is the police officers, before a wrong thing is going to happen, this police officer comes to know and then catches them. And what happens one day, somebody comes and catches Tom Cruise itself. That's how the story goes. So this is something which GD talked about, hypotension prediction index. So this monitor is around 40 lakhs and the sensor which you have to use is around 26,000. It has to be attached to the arterial pressure. So what it does is, it takes the mean arterial pressure. You see this waveform? So this waveform, there are 26,000 features which was extracted from this waveform, and that AA algorithm reduced the 26,000 to 26 features, and from that 26 features it calculates the value. If you see that value here, HPA, it is 92%, which means in the next 10 minutes there is a probability, 90% probability, that this patient will have a blood pressure recording less than 65 millimeters of mercury. So you have some time to think what could have gone wrong. And again, this is also not 100% accurate. When you start using it, you will know plus and minus of it. But then, to a major extent, it works. So if I know the heart rate, if you see here, HPA is 65. This means the chance of his development of hypotension less than 65 is only a 60% probability. So you have to start acting when that HPA index goes above 85. So that is what it is. So hypotension prediction index. The details the previous speaker has spoken. This is just. Number one, what is the problem? It all depends upon this arterial pressure waveform. Okay. Now comes this. So all these are from patients. You look at the morphology of the arterial pressure waveform. Okay. So is everything is correct, or is everything wrong, or whether it is a variation? There are so many factors. So we know this is the dicrotic notch. Okay. You say anything before the dicrotic notch, the area under the curve, that is the stroke volume. The pulse vessel stroke volume. So here you see where is the dicrotic notch. It has already come down. Okay. Here you see two waveform because the SVR is so low. The diastolic is coming as a one more waveform. So what should the algorithm take? Which is the systolic, which is the diastolic? Which area it should cover? And here you see the first notch is less, the second notch is here. So which notch it should take as a dicrotic notch? So this is where the variations happen. So sometimes the machine will not predict as it expect to predict. So all these are differences. How this is accounted for in the algorithm, nobody knows. Whenever a company makes a software, they make it proprietary, so nobody will know how it makes the algorithm. So this is what I want in AA. Okay, this is the Google Glass. Now it has been stopped manufacturing. We all do ultrasound procedures. Okay, so here is the ultrasound machine. Here is the anesthetist doing it. But I am not seeing the needle, I am just seeing the ultrasound machine. And suddenly I will stop seeing the needle, then I look down, because of the jelly it would have slipped down. Then again we have to readjust. Because I am seeing there, I am seeing this. And one more monitor I have to see, which is the ECG, whether arrhythmia is happening or not. Okay. So I have a Google Glass. If that ultrasound image is fed into my Google Glass, so I just need to see only the patient because that image is reflected into that screen. Okay. The same way the monitors. So some anesthetists might need to cover 2 or 3 operation theatres. Now how do I see all the 2 or 3 monitors? So everybody has worked WFH, work from home. If I have a Google, at least I can do work from office. I can see all the monitors projected onto the screen. And if you have an AA, because we know which values are above. See, heart rate, if more than 100, I should do something. Less than 60, I should do something. We can define the limits. And whenever the patient value goes beyond the limits, then that should pop up. So that can be designed. So if I have 10 patients, that's what happens in the IC. I have 20 beds, I have to see. I cannot keep looking all the 20 beds. So something goes wrong, that one pops up. So then I know, okay, I have to go to that bed and see. So that is how we can use. Still time is there? Okay. This is another thing, not AI, not this one. So this is actually the probe and there is a magnetic. You can neuro-navigate your needle itself. Okay. So next is EEG. Whenever you want me to stop, I will just stop. There's another 10 slides is there. So where does the EEG occur? In the brain, there are 6 layers. So from the pyramidal layer, we know any cell, the action is by movement of sodium and potassium. Positive becomes negative, negative becomes positive. There is a movement of electron which is the current flow. So that is picked up by placing an electrode over the scalp or directly over the brain. You get EEG or electrocardiogram. But then brain does not work individually. It is a circuit. So from one lobe is communicating to the other lobe, from the frontal to the parietal, parietal to the occipital. So it is a circuit, which means what? Suddenly my slide goes off. Now what is the cause? There could be some problem in the screen. There could be some problem in my computer. There could be some problem in my connection. There should be some problem in the audio visual. There could be some problem in the electrical supply. There is some problem in the transformer. So we do not know. Any one way there is a disruption, it goes off. So similarly in the circuit, if any one thing is disrupted, the patient will become unconscious. So you cannot say this point means he is conscious, this point is unconscious. So it's very difficult. It is a circuit. So mostly the attention, the execution, everything happens in the frontal lobe. And that is the reason we keep all our depth of anesthesia monitor in the frontal area. It is not just because hair is not there, it is easy to fix the sensors. Okay. Sometimes we get bored, we can put sensors anywhere. But then forehead is chosen because most of the executive functions happens in the frontal lobe. So that is why we monitor the forehead sensors. Now this is like EEG, raw EEG, this is how it looks like. This is a time and this is an amplitude. This is in microvolts. Now this EEG can be split into multiple sine waves. So these are the different sine waves I have just drawn to for example. Once you draw this sine wave, then it is easy to do a fast Fourier transformations. What happens in the fast Fourier transformation? The x-axis becomes the hertz. That is the number of cycles per second is 1 hertz. And here it becomes the power, that is microvolt square, that is twice the amplitude. Now I can do a mathematical calculation, plot x versus y f of t. Then it will tell you in the 4 hertz this is the power, in 12 hertz this is the power, in 16 hertz. So from this I know a majority of the EEG is within this 16 hertz. 16 hertz means somewhere in the alpha. If it is less than 4, if this peaks, then it is in delta or theta. So that is how we say. Then it becomes easy for any monitor to do further analysis and derive the numbers. So for any monitor, you need the input. Input is the EEG, the source electrodes. Okay, that is only going to take the data from the patient. Then you have this processing algorithm. There are so many algorithms available, new ones, old ones, fast Fourier transformation, bispectral index, fuzzy logistics. There are so many available, nonlinear regression model, so many is available. And then output. Output is what we see in the screen, which displays the parameters. Now where does things, some monitor picks up very fast, some monitor does not picks up. The thing is, many of the companies will determine the output. That might not be user friendly to us. So we try using it, it fails, then it goes to the storeroom. So when the engineering and the medical group sit together, we can tell what we want and we can tell how we can collect the source. Algorithm portion we should leave it to the engineers. So these are the different type of electrodes which we routinely use. Okay. This is the cup electrode, non-invasive. This is needle electrode. This is a corkscrew electrode. It has different applications. Now these are the few of the monitors already in the market which is available to monitor the depth of anesthesia. This is the bispectral index. It converts into the FFT, then it do some sync fast low, which is a beta ratio calculation, then it calculates the burst suppression and then frequency domain. It derives the number. How it derives the number, nobody knows. Okay. Now this is the QNOX monitor. Again, is another monitor which works on the fuzzy logistics. This is an entropy which is based on third law of hemodynamics, that is a randomness. Okay. Normally we think so many things. So now in the audience, it's not necessary everybody is looking at my screen. Somebody will be thinking of lunch, somebody might be thinking what to do in the evening, somebody will be opening eyes and then sleeping, somebody will be doing in the WhatsApp image. So many things happen simultaneously. So the EEG is very random. So the value will be 100. Okay. As you give drugs, patient goes to sleep, it becomes uniform, synchronized. So mainly you see alpha and theta, your entropy value comes down. Suppose if I apply ECG, entropy to the ECG, it will be 0 because it is almost regular. Okay. Of course, some heart rate variability is there, it not be exactly 0. Okay. The opposite is EEG, 100. This is a patient state index. Again, this is from the Massimo group, and this one is a narcotrend which does only the analysis of the EEG with relation to the sleep pattern and gives a value A to F. And this is the cerebral state index. This is a Wi-Fi system. You connect the sensors and the machine. There is no wire connecting in between. So this is how we apply the sensors. This is the entropy sensors, the sticky sensors. And here we have used the ECG itself as a sensors. This is the BIS sensors. Most of all these sensor type are called as zip prep electrodes. They have a unique feature. They have a gel inside and they have some spiking sponge, because the stratum corneum offers a lot of resistance. So when you press the BIS sensor, always you press in the middle of the sensor so that it pokes in and then it goes below the stratum corneum so that the signal gets captured. Okay. Even depending upon the module we use, we can also use the ECG. This is what the Costco electrodes. We use the Costco electrode not connected to monitor because we do EEG, we do evoked potential monitoring during the brain surgeries. So during surgery I cannot go near this because everything will be fully draped. I want something which never comes out. So we use a Costco electrodes. This is one module from GE where you use this electrode, and this is the module, and this is the output waveform we get. So this is as far as the source. So this is the interface. So each module has a different interface. This is for BIS, where the signal processing happens. A lot of things have to be done before algorithm kicks in. Filtering, artifact, all those things must be removed. So I will just go through some pictures and wind it up. This is the raw EEG and this is the density spectral array. So where you see red color, that is 0 to 4. So in this patient, the predominant EEG pattern is less than 4 Hz. And there is one more pattern which is seen at around 15 to 16 Hz. So by looking at this itself, we can say which drug the patient is receiving. Most of the inhalational anesthetics will have a dark band here. Most of the intravenous anesthetics will have 2 bands here. So if suddenly one band goes off, that means patient is having arousal. So even without looking at the number, we can make an interpretation. So that is why you should always see the number with the waveform. Because how do we know whether it's artifact or not? Suddenly the number will go up and you think, oh, patient is awake, you push one more drug. Okay, that is not required. Fine. So here you see these white lines. So these are all the artifacts corresponding to this. The number might still look the same, but then you see the lot of artifacts. I wouldn't depend on this number to make a decision. I will wait for this artifact to subside like this and then come. Here you see 34, here it is 49. Okay. So you must see the raw waveform before you make any interpretation. So this is something burst suppression where you see a flat line EEG followed by the burst. This also you can see entropy, you can see EEG monitor in all monitors you can see. So this we achieved at a MAC of 1.8. Normally we don't give that much. For specific conditions we give. Suppose elderly patients, normally we give 0.8 to 1 mark. So even at 1, that's what normally we give. So if you see this burst suppression pattern, that means his brain is very sensitive, we must not give that much drug. Then the post-operative cognitive problems are more. But if I don't have this monitor, I will not know. For every patient I will give 0.8, for every patient I will give 1 mark. So that is how the outcomes differ. So this is with isoflurane. This is a raw EEG. This is how it looks like, burst suppression. This is with entropy. This is with other monitors. So not only that, you see EMG 26%. This is very, very important. If the EMG is more than 50%, that this number is not reliable, because that waveform and the number is derived from the EMG rather than from the EEG. So you should not make any decision based on this. You see this artifact here? This is because of the stimulus which we give for evoked potential. So luckily this has an inbuilt algorithm. It has itself identified as artifact. And you see that EMG, it is 100%. So all these must be included in the development of the machine to differentiate. It should tell that this number is not reliable because this is an artifact. This is again one more artifact which is a slow wave. So this is the blink reflex. See, periodically it is coming. So the blink reflex. But it didn't say that this is an artifact. Okay. So you must correlate with the clinical conditions. This is the electrical interference artifact, 60 Hz artifact. Okay. You see this flat line. This is not EEG. Okay. But if this gets imposed onto the EEG, then the entire waveform will change, the number will change. Again, these are a few artifact images. Even painting and draping here, you shake the head, no, while painting, draping, it causes an artifact. But these things the machine will not know. Only we can know and we have to interpret. This is a ECOG, which is an image taken from the brain, not from the scalp. This can be used in the ICU also. So this was a patient with a seizure where we used isoflurane in the ICU, and using that ICU monitor which has a module base, we can see the burst suppression. These are, thank you.
Thank you, Professor, for sharing such a wonderful knowledge. Ladies and gentlemen, it's now, we have a shortage of time, so we'll have a 15 minutes lunch break. Lunch will be served in the dining hall over there. So all are requested to proceed for the lunch. Thank you.
Join her. I'm the one. Prime Minister. 싫어.
Collar mic.
원래는 하여분이 또 그래. 방으로 먹는다. mỗi dầm đất của nó mạch cái này bao nhiêu à kata apa color mic dari pun tahu Kau sejak masuk ke Manipur, itu tong. Ini apa? Cara. 한국말을 잘. 아. 그런데 뭐를 야구에 있는 게 있어. 여기 있는 좀 있는. YouTube está horrible, está horrible. Está horrible. Mana lagi? Mana itu? Mesti kita. Ini tahu kan? Saya aja begini. Si mayau tak tu, haram berapa?
Hello? Am I audible in the back? Hello? Hello? Yeah. Okay. It's okay? Yeah. Hello. Hi. So, thank you for this invitation. And so thank you for this invitation. I'm Kshitij. So I just put this slide up to show this rather unconventional journey that I've had, ultimately landing in between healthcare and artificial intelligence. I did my MBBS and MD from Mumbai. I did a PhD in neurosciences in Switzerland and the US put together. And along the way, I started doing machine learning truly just for fun, right? So I was decently good at statistics, and I said, okay, I'll also try to do machine learning. And I started doing machine learning. I'm not officially trained in machine learning. I just learned it by myself, and I started doing it to analyze my neuroscience data. And when I was coming back to India, the Koita Center for Digital Health, which is a new research center at IIT Bombay, was looking for a doctor who understands machine learning. So I became their first full-time faculty. And my mom always told me that don't do two things at the same time. And we being Indian children, I basically defied that advice. Right? So I am at the intersection of artificial intelligence and healthcare. And there are two specific things that I will talk about. One is my deep interest in data efficient machine learning. And the first part of the presentation will be about medical data efficient machine learning, and the second will be on the clinical applications that I do using machine learning in the healthcare space. So what is medical data efficient machine learning? And we heard a lot about AI/ML since the morning, and there is a common theme in artificial intelligence and machine learning that a lot of people talk about, and they say that you require a large amount of data, and without